Your brain is constantly lying to you about the world, and I can prove it to you. You are given a choice. You could live in a city with an average income of $50,000 or $100,000 per year. Which would you choose? If you instantly chose the second city with no hesitation, then you just fell for a statistical fallacy, and almost everybody does. And by the end of this video, you'll understand why averages can quietly mislead you and how to stop falling for it. At first, you might try to argue you'll earn double in the second city, but here's what that number isn't telling you. That average could be inflated by a handful of extreme earners. These are individuals who could own multiple yachts, while everyone else in both cities earns roughly the same, working the same types of jobs. Now, you may feel like I set you up to fail with that example, but the real issue isn't the city's average pay. It's that this is often the only information we are given, especially in a headline. When we are given a single number or statistic, we automatically assume it represents most people. This is why companies miscalculate demand, why cities misallocate resources, and why we are consistently misled when given only partial information, like a simple average. When we see a number, our brains naturally try to fill in the rest. To understand why this keeps happening, we need to look at what the average actually tells us and what they actually hide. Imagine you are 25 and starting your master's degree. You're told that the average age for your program is 26 to 27, and so you expect most people to be around your age. But when you walk into the room, most people there are actually in their early 30s, and some in their early 20s even. Almost nobody is the same age as you. In this case, the average ends up sitting between two clusters of students, younger and older. Now when we look at the median, which is the age that splits the group in half, it turns out to be 30. Now, while that's closer to what the room feels like, it still hides an important detail: the pattern of ages. If most people are 30, then the most common age, or the mode, would also be 30. If you had mean, median, and mode together, you would have had a much more accurate expectation of your class's age distribution. You would have known, while the average age is around 26 to 27, most people would be 30, and some younger students are pulling it down. These numbers collapse a messy reality into a simple and easy to understand number. While it works for an estimate, it does not capture much of the patterns of information, unfortunately, and can lead to misunderstanding the data. To help make our understanding of data distributions more complete, something that would be very useful to know as well as the average is the spread of the data, or variability. The spread of data, when paired with the average, actually gives us a lot of information. If you knew the average age was 27 with low spread, then most ages would be clustered around the average and are close to 27. If there was high spread, however, then you would have known that there's a wide range of ages, and most people would not be around 27. The same could be said for how well you perform in school. When discussing performance, it is often difficult as well as time consuming to explain how you did in every single course. An easier and super common metric used is GPA. It looks at how you did in all your courses and displays that information into a simple compact number. If we were looking at average GPA of two students, you would be able to distinguish who did better on average. Let's assume their scores are 2.9 and 3.8. Now, you'd expect on average the 3.8 student to do better in their classes, and they do for the most part. But are we really comparing apples to apples? What if that student who got a 2.9 took courses that were substantially more difficult, or they did pretty well on most but really bad on a few, especially in their first or second year? Is it fair to say that they objectively did worse when they didn't even take the same courses? You could have all three of the metrics, mean, median, and mode, but they wouldn't tell you much else that the GPA already tells you. This is why it is critical to understand the data as well as the metrics. Blindly listening to a simple metric often leads to a significant misunderstanding, and is why most colleges for grad school only look at your best 2 years in extracurriculars. So you might be thinking, why do we use averages at all then? The fact is they are pretty useful, but in certain contexts and thought about critically. From our first example, it is clear that you would want to make sure the data is not heavily skewed with large outliers on either side. This is what would have saved us from blindly choosing the city with the highest average salary. Let's visualize the housing prices on the screen now. You can see that most are actually pretty close together, but all the way to the extreme, you can see the outliers we mentioned before. This is what's skewing our data right now, and you can see the average is far away from the median and mode because of it. You might be thinking, why don't we just remove the highest and lowest people who are too extreme? And we certainly can. It actually is a special name known as the trimmed average. If we got rid of the extreme outliers on both ends, the average house price would have been much more representative of what it should have been. Looking at the new trim distribution, we can see that the average moved much closer to the median and mode. The distribution now shows you a much clearer picture of the actual housing market. With an even distribution of data, you would also ideally want as little spread as possible, as this makes it that even if we remove the extreme outliers, you don't end up with an average house price of $500,000 when no one actually owns a $500,000 house, similar to the grad school average age example. So far, this might seem a little abstract with all the talk regarding averages, spreads, and data distributions. But this kind of mistake isn't something that only happens in textbooks or policy decisions. It shows up in small, everyday choices we make all the time, often without even realizing it. For example, how many times have you been scammed from online shopping? The reviews looked good, the pictures weren't great, but they weren't too bad, but as soon as you got it, you knew it wasn't it. Imagine you were looking to buy a new headset to replace your old one, and you were looking to purchase the one with the best reviews. After scrolling for a while, you noticed most were around 3 stars, but then one was listed for 4.2 stars, brand new and even on a sale ending soon. At first, it might seem like the obvious choice, but instead of purchasing it right away, you look at the reviews and are shocked. A surprisingly large portion were actually negative, with a rating of around 1 to 3 stars saying the quality is bad, the fit is off, or the actual speaker in the headset broke down after a couple weeks. What is weird though is how many generic 5-star reviews there are that don't actually tell you much about the product at all. When you look at the actual numbers, a quarter of the people did not like the product. This is quite significant, showing a cluster of negative reviews, and puts it into perspective. Would you buy a product a quarter of the people didn't like? On the surface, it seemed like the best one, and at a great price too. But looking into the data before purchasing, it was clear that it was too good to be true. Some may have reviewed it too soon after opening, or might just have left a generic review. More people also would have helped, as it would have helped uncover hidden patterns. This is why it's useful to know the spread of the data you are given. If most of the reviews were clustered around 4 stars with hundreds of reviews, that indicates the product is probably pretty good, and you can expect the same level of quality as everyone else. If it is evenly spread with about 50 reviews per star, you might experience a product which varies in quality, and you might want to be a little more wary of that purchase. It could have been amazing, or something you returned an hour later. And there we have it. You've gained some extra skills in your statistics toolbox. Now, next time you see a flashy number, whether it's an online review or average house price, remember the 3 questions we now have. Do we need the mean, median, or mode? Is the distribution skewed? And what is the spread or variability telling us? When you ask these questions, you stop your brain from filling in the data and start seeing the real story. If you enjoyed this video, make sure to check out the recommended video on the screen. You'll probably like it as well. Make sure to like, comment, and subscribe as well.